These are solutions to our third quarter exam review assignment. So first we've got some of our derivative rules. In one, the derivative of a constant. Remember, this would be the same as a horizontal line. So the slope is always 0, derivative of a constant. If you wanted to explain that as a power rule, you could start with a constant times x to the 0. In number 2, the derivative of 1x. So we could just write 1, and again, if you wanted to explain that with the power rule, start with 1x to the first power and bring your power rule. And number 3 is our power rule. We bring n in front and we reduce the exponent by 1. 4 is the derivative of a sum is the sum of the derivatives. So you could write the Leibniz notation, or you could just write f prime plus g prime. So we take the derivative of each part individually. Likewise in 5, with the derivative of a difference, we take the derivative of each term separately. In number 6, the derivative of a constant multiplier times the function. We can bring the constant out in front of the derivative. So we don't do the derivative of the constant comes in front, and then we would do the derivative of f prime. 7 is our product rule. So we take f of x times the derivative of g plus g of x times the derivative of f. 8 is our quotient rule. Let me scroll to get some more room here. So we want low d high. So we want g of x times the derivative of the numerator minus the high function times the derivative of the low function. And I guess we don't need 2 sets of parentheses there. And in the denominator, we want the low function squared. All right. And then we have the derivative of e to the x. This was the last thing we talked about. Remember that the derivative of e to the x is the one function that is its own derivative. So the slope here appears to be 1. The slope here at e is e. The slope over here is 1 over e. So the derivative of e to the x is e to the x. Number 10, I wrote the formula here. This should actually be the derivative. This is a little typo here. This should be a to the x power. So the derivative of a to the x, similar to e to the x, but we have to multiply by the natural log of the base. And we'll talk more about that later. That one will not be on your quarter exam. The derivative of sine we know is cosine. The derivative of cosine is opposite of sine. Derivative of tangent is secant squared x. Derivative of cotangent is negative cosecant squared x. Derivative of secant is secant times tangent. And derivative of cosecant is the opposite of cosecant times cotangent. And you could practice those with the quotient rule, but it will save you time if you have them memorized. All right, in number 17, we've got our theorem. As theta goes to 0, the limit of sine theta over theta is 1. 18, we've mentioned this a couple of times, but we haven't used it much. The derivative, we can prove this using 17, but this derivative goes to 0. And I doubt that I would put that on the quarter exam since it hasn't occurred too often in our homework yet. All right, filling in our delta epsilon tolerance. So if we choose, and it doesn't matter what letters you use here, so if our limit as x goes to a of our function is L, then we know that there is a limit if, no matter what distance epsilon, no matter how small epsilon gets, so you want to stay within L plus epsilon and L minus epsilon, you can find a distance delta that would keep you there. So this value would be a minus delta, and this would be a plus delta. So we can write that information if x is chosen within a delta tolerance horizontally, then f of x should lie within an epsilon tolerance of the limit vertically. And we can write that two different ways. First, using distance. Remember that the distance between a and b is the absolute value of a minus b, or b minus a. You could subtract in either order. So whenever you see distance between 2 points, remember you need to put it in absolute value. So we want to say if the distance between x and a is less than delta, then the distance between f of x and the limit L will be less than epsilon. And in 22, the alternate form is to use our interval notation. An element of is that curly E shape. If we choose x so that it is an element of the interval from x minus delta, let's use a as our specific value of x. So if you choose an x between a minus delta to a plus delta within that horizontal range, then we can guarantee that our f of x, our y coordinate, will stay within the range from the limit plus, guess we want small to large, right? Minus epsilon to limit plus epsilon. So 21 and 22 are synonymous. All right, 23 is some practice using our calculator. So we want to first go to our y editor, and we want to put in this function, the square root of x plus 1, as our y1 function. And now we want to talk about the limit of f of x as x goes to 3. Well, think about putting 3 into the function. Here it's continuous, so we could just find that limit by direct substitution. So there's no question about the value we're interested in here. So our a value is 3, and our limit we know is 2. But now our question is not can we get to that limit exactly, but can we stay within 1,000th as our epsilon challenge vertically. So again, I'm just going to ignore these numbers here, and I'm going to make a fairly large tolerance window here. So I'm going to use this as my epsilon value. So this would be our L plus epsilon, and we know this coordinate is 2, so we want to set this as 2.001 on our calculator. So put that as your y2 function, and I'm ignoring this value as well, just so that our picture isn't quite so cramped. So I'm going to use this as our lower value, so I'm going epsilon units down. So this would be at y equals 1.999. I'm staying within 1,000th of our limit of 2. So I'm going limit plus epsilon, limit minus epsilon. And this is a very exaggerated diagram again, so ignore these tick marks. We're not using the size of this graph. I've really exaggerated. So if I can stay within these values, so this distance would be our delta 1, and this distance would be our delta 2. And if they turn out to be different, then of course we would choose the smaller of those two delta values. So what we need to do on our calculator, so you've got this graph as our y1 function, and we're going to have this horizontal line as y2 and this horizontal line as y3. And then you have to go through your steps. Remember that in the math menu, which is F5, you want to choose option number 5, which is to find the intersection of 2 points. And I think we've done this in class a couple of times, so I'm not going to pause in the video to do this. See me if you do have questions about it. But remember that you have to answer 4 questions. First, it will say, is graph 1 in your window of your calculator? Remember, it shows you the function number in the upper corner. And it will start with function 1. Is function 1 one of the graphs you're looking for the intersection of? And you would hit enter to say yes. And then it would change to function 2, and you'll hit enter. And then the third question is to move your cursor to a lower bound. So you would want to move your cursor below the intersection point and hit enter. And then it'll ask for an upper bound. So move your cursor to an upper bound on the right-hand side of the intersection and hit enter. And then it will give you the coordinates of this intersection point. And I've already written that down. This, we know the y-coordinate, of course, is 1.999 because it's on a horizontal line. So this coordinate turns out from our intersection. And I've kept lots of decimal places. And then we repeat the process with our functions y1 and either y2 or 3. You use the up-down arrow to change that function number. Repeat the process, and this x-coordinate turned out to be 3.004 with some zeros behind it. So it's not always this symmetrical, so remember to choose the smaller of those two distances. So here we would want to choose our delta value to be 0.004. Our question might not ask for a delta value. If our question asked for the interval, let me spell that correctly, if the question simply asked for the x interval that we should stay between, then we would want to say that we want to be between 2.996 to 3.004. So it depends on the wording of the question. If you're asked for delta, choose the smaller of those two distances. Or if you're asked to choose the x interval, that would keep you within the y interval. So if I use a highlighter, the idea here is as long as we stay horizontally between those two x's, then our y-coordinate will stay vertically within our safe range with our tolerance on the vertical limit.